Okay, let's talk about a word that sounds, well, kind of scary. Stoichiometry. But what if I told you it's something you already do, probably every single day, in your kitchen? Stick with me, because you're about to see that chemistry is a whole lot like baking a cake. Let's get into it. You look at a chemical equation with all its letters and numbers, and it's totally normal to feel a little lost. It can seriously feel like you're trying to read a language you've never even seen before. But here's the secret. What if it's not a foreign language at all? What if all those complicated-looking equations are just recipes? Simple, step-by-step instructions for making something. That's really all stoichiometry is. It's the recipe book for the entire universe. All right, let's jump right in. First up, the number one rule of any kitchen, and as it turns out, any chemistry lab too. It's got a fancy name, the law of conservation of mass. But honestly, all it means is that you can't make stuff appear out of thin air. If you put 500 grams of flour, sugar, and eggs into a bowl to make a cake, you can't magically end up with a 1,000-gram cake. The weight of your ingredients has to equal the weight of your final dish. Simple as that, right? So who came up with this kitchen rule? That would be this guy, Antoine Lavoisier. Think of him as the master chef who, way back in the 18th century, figured this whole thing out. He's often called the father of modern chemistry for this exact reason. And he said it perfectly himself. Nothing is created, an equal amount of matter exists both before and after the experiment. He basically laid it all out. You start with a certain amount of stuff, you're going to end with that same amount of stuff. That's it. This is the one rule in our chemical kitchen that we just can't break. So if chemistry is just cooking, then how in the world do we actually read the recipe? Let's break down how a chemical equation is really just a recipe card. Okay, get ready for the aha moment. Take a look. On the left, we've got a recipe for a grilled cheese sandwich. Super simple. On the right, the chemical recipe for making water. But look closer. They're set up in exactly the same way. You've got your ingredients on the left, a plus sign meaning and an arrow pointing to what you made. See? It's the same language. Not so foreign now, is it? So let's break that down. The stuff you start with on the left, those are your ingredients. In chem speak, we call them reactants. The final dish you get on the right, that's your product. And those big numbers in front of everything, those are the coefficients. They're just the amounts, telling you how much of each thing you need, like 2 slices of bread or 2 hydrogen molecules. Okay, so this is where people can get a little tripped up. A really common question is, why do we change those big numbers, the amounts, instead of the little numbers that are part of the ingredients formula? And this is so important. Changing that big number out front, the coefficient, is just like saying you want to make 2 of something. So 2H2O is just 2 separate molecules of plain old water. But if you change that little number, the subscript, you're not changing the amount, you're changing the actual ingredient. H2O2 isn't water anymore. Nope, it's hydrogen peroxide. That's like the recipe calling for sugar and you use salt instead. The result is, well, completely different and probably not something you want to drink. All right, so we get the recipe part, but there's a problem. How do you measure out ingredients that are so tiny you can't even see them? I mean, you can't just count out individual atoms. So chemists came up with a really clever unit to help with that. The thing is, atoms are just ridiculously small, and there are billions and billions of them in everything. Trying to count them one by one would be like trying to count every single grain of flour before you bake that cake. It's just impossible. We need a better way. And here's the trick. It's called the mole. Now, don't get weirded out by the name. A mole is just a word for a number. Kind of like a dozen means 12. A mole just happens to mean a gigantic number. 6.02 times 10 to the power of 23. That's called Avogadro's number, and it's basically the chemist's version of a dozen. And this is why the mole is so unbelievably useful. It's like a bridge. It connects the world of the recipe, which is all about individual atoms and molecules, to the real world of our lab or our kitchen, where we use scales and measure things in grams. The mole lets us weigh out a massive number of atoms without ever having to actually count a single one. It's a total game changer. All right, so far we've been imagining we have a perfect kitchen with unlimited ingredients. But you know how it is in real life. You're in the middle of making something, you reach into the fridge, and you're out of a key ingredient. What happens then? Well, that one ingredient you run out of first, that's what we call the limiting reactant. Let's go back to that grilled cheese. Say you have a whole loaf of bread, but only one slice of cheese. How many sandwiches can you possibly make? Just one, right? The cheese is the limiting factor. It limits how much grilled cheese you can end up with.
And finding the limiting ingredient in a chemical reaction is pretty much the same common sense. Step 1, you read the recipe, that's your balanced equation. Step 2, you check your pantry, you figure out how many moles of each ingredient you actually got. And step 3, you look at the recipe's ratios and figure out which ingredient is going to run out before the others.
Okay, we're on the home stretch. We've followed the recipe, we've figured out our ingredient limits, and we've cooked our dish. But here's the question. Did we actually make as much as we thought we were going to?
Well, in chemistry, we have names for these two things. The theoretical yield, that's the perfect world result. It's the maximum amount the recipe says you should be able to make. But then there's the actual yield. That's what you really get in the lab. You know, in the real world where maybe you spill a little or the reaction doesn't quite finish. It's the difference between what the cookbook promises and what's actually on your plate.
So, recipes, ingredients, yields. Okay, but why does all of this matter so much? I mean, who cares if you're a little off?
Well, take a look at this, an airbag. That thing doesn't just pop out of nowhere. It's the result of a chemical recipe that has to be calculated with absolute perfect precision. This isn't just baking a cake anymore. This is stoichiometry, where getting it right saves lives.
So here's the deal. Inside an airbag, there's a solid substance called sodium azide. When a car crashes, a tiny device sets off a reaction that turns that solid into a huge amount of nitrogen gas, like instantly. And that gas is what inflates the bag. The amount of sodium azide is the limiting reactant, and it has to be measured perfectly to produce the exact volume of gas needed. If they get that recipe wrong, it could be a total disaster.
And that's really what stoichiometry is all about. It's the science behind the recipe. It's not just in a lab. It's what makes a car's airbag work. It's what makes a baking soda volcano fizz. It's happening all around us all the time. So the question I'll leave you with is this. Now that you know the secret, what recipes are you going to notice out in the world today?